Now that we've defined Riemann sums, we can define what it means for a function to be Riemann integrable, or simply integrable. Remember these two pictures. The one on the left represents the lower sum with respect to the given partition, in which the heights of the rectangles are determined by the infima of the function in the subintervals, and the one on the right represents the upper sum, which uses the suprema. We'll use these in the next definition. A Riemann integrable function, which in this context we often shorten to integrable function since there's no ambiguity, on the interval from a to b is a bounded function f, such that this equality holds where these limits are taken over all partitions P of AB, and M of P is the mesh of P. Remember that the mesh is the width of the widest subinterval. We call this common limit the integral of f on AB. We denote this using this notation, which is read the integral from a to b of f of x dx. We call f of x the integrand of the integral. Note that we haven't defined integrals for unbounded functions, such as f of x equals 1 over x, on the interval from -1 to 1. Let's look again at these graphs. Notice that for any partition P, the lower sum is always bounded above by the upper sum. Not only that, but the gray area that we're trying to find is always between these two, regardless of what partition we choose. We're using the idea behind the squeeze theorem to define the area. If it's stuck between these two expressions, the lower sum and the upper sum, and those converge to the same limit, then the thing between them must be equal to that limit also. This has a significant practical implication, since for a fixed partition P, every Riemann sum formed using that partition is between the corresponding lower and upper sums. This means that to determine the area, it doesn't matter which approximations we use. As long as the meshes approach 0, the result will approach the area. Usually the simplest option is to divide the interval into equally sized subintervals and use endpoints to determine the heights of the rectangles. Think of dividing the interval AB into n subintervals of equal width. Since AB has width b minus a, this means that the subintervals all have width b minus a over n. So we get this. The integral from a to b of f of x dx is equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of a plus I times b minus a over n times b minus a over n. You should check that the expression inside the function is the expression for the right endpoint of the ith subinterval. Let's look at an example. Suppose that f of x equals x squared on 0, 3. Let's find the integral of f on 0, 3. We'll first do some work to simplify the expression within the limit. First, replace a and b with 0 and 3, and then simplify this expression by pulling out everything that doesn't involve an I. So the sum becomes 27 over n cubed times the sum from I equals 1 to n of I squared. We have a nice formula for that, so we can write this without a sigma. Let's also switch the places of the terms in the denominators. This doesn't make a mathematical difference, but it's nice to group all of the terms involving n in one place. So the integral of f is the limit as n goes to infinity of the sum from I equals 1 to n of I times 3 over n quantity squared times 3 over n. And by the work we just did, this equals the limit as n goes to infinity of 27 over 6 times n plus 1 times 2n plus 1 all over n cubed. We can treat this in exactly the same way we would treat the same expression involving an x instead of an n. Ignore the 27 over 6 for a moment. The rest is a ratio of two polynomials of degree 3, so the limit as n goes to infinity is just the ratio of the leading coefficients. That means that the limit is 27 over 6 times 2 over 1, which simplifies to 9. It's worth noting that these techniques are often unnecessary, especially when dealing with polygons and circular regions. You should always choose the best method for each problem you're dealing with. Let's finish with some properties of integrals. First, the integral of a sum is the sum of the integrals. Second, a constant multiple can be pulled outside of an integral. And third, an integral from a to b can be split into two pieces, one piece from a to c, and the other from c to b. It isn't strictly required that c be in the interval ab, as long as f is integrable on an interval containing c and the interval ab. These properties can all be interpreted in terms of properties of areas. There's another such property, and we'll end by talking about that. Consider this region. If we shift the entire thing horizontally by c, then the area hasn't changed. The new interval goes from a plus c to b plus c, and remember that to shift a function to the right by c, we subtract c from the argument of the function. This means that the integral from a to b of f of x dx is equal to the integral from a plus c to b plus c of f of x minus c dx. We saw something similar when we manipulated the indexing of a Riemann sum to make it easier to determine. This property says simply that areas are unchanged by shifting.